sorry, I just had to go get a different marker that's going to actually show up on the paper. So like I said, our constant is our source voltage, 120 volts. So whatever's across resistor 1 will be the same voltage across the motor, same voltage across the capacitor, right? The difference is the currents are out of phase with each other. So we need to add all of our variables vectorially, which is what I'm doing with our triangles, right? So the triangles for the resistor are all in phase, so just a horizontal component. The motor is flipped to what it would be in series because now I'm referencing from voltage as my constant, right? So there's a motor that has 18 amps of current flowing in it, 0.3 lag. So it isn't a pure inductor. So that means it has a variable of resistance in it as well as inductive reactance. Therefore, it has its own impedance. The current triangle is going to be the same. And then the capacitor is always pure and it's always drawn in vertical position, 90 degrees out of phase with the XL component. And it's drawn in the upright again because this is parallel. So you can see that I've X'd out my impedance total triangle because in parallel we cannot use an impedance total triangle. We are limited to only using the impedance for the branches, right? So now I'm going to take this information and populate it into my triangle. So my incoming current for the circuit is 18 amps. So that would be found here. That's my I total, right? So that's the vectorial sum of all of my in-phase current vectorially added to my IXT. I've drawn my triangle in the downward position because I know it's lagging because it told me it was, meaning my IXL is greater than my IXT, or XC rather, so that IXT is lagging. So my I total is 18 amps, so I'm going to put that in there. Okay, the resistor has a current flow of 9.2 amps, so that gets populated right there. Then the motor current, so they're telling me the current that's flowing through that motor is 18 amps. So it's important that you're putting that on the hypotenuse of your motor current triangle because essentially your motor is just a series circuit contained with 120 volts across it. The resistive portion is 90 degrees out of phase with the inductive portion, so I cannot just take those currents and vectorially add them together. They're out of phase with each other. I don't know how much voltage is across the resistive portion. I don't know how much voltage is across the inductive portion. So whenever they give you the incoming current for the motor branch, that is always going to be the hypotenuse. Now they tell me the power factor, and that is the relationship between my in-phase current and my vectorial sum, right? So that's a 0.3 power factor. And I know if this is the power factor of my current triangle, that will be the power factor for all of my motor triangles, right? Okay. So now that's the motor information. I don't have anything on the capacitor. So now this is what I'm left to work with, and I need to dial back. Ultimately, I'm trying to get to here, all right? So now I'm going to start populating the triangles based on what I have. So most of the information is pertaining to the current triangle, so that's what I'm going to work with. I know the incoming current on that motor is 18 amps, and I know the power factor. So I know the in-phase current is going to be less than 18 because the hypotenuse is always the greater value. So I can apply that by using my power factor to solve my IRM. So 18 times 0.3 gives me 5.4 amps. So 5.4 amps is the in-phase current for that motor. And then to find my IXL, I would just use Pythagorean, right? So 18 squared minus 5.4 squared equals, and I square root that, so I get 17.171 amps for my IXL. All right, so now I have an in-phase current flowing through the resistor that's at 0 degrees. That's in phase with the current that's flowing through the resistive part of my motor. So those two values of current are at 0 degrees. So we've learned previously that any currents that are in phase with each other are additive together, right? So I can take those two values to populate my IR total for the circuit, right? So my IR total equals IR plus IR motor. So the current flowing through the resistor is in phase with the current flowing through the resistive part of the motor. So that's 9.2 amps plus 5.4 amps for a total of oh, Christ's sake, sorry, these nails. So that's 14.6 amps. So that then would get populated in the bottom part of my circuit total, 14.6 amps. So now I can find my IXT. IXT is the resultant between IXL and IXC. And I know that IXT is lagging, which indicates that my IXL is greater than my IXC, which is going to be very important when I'm working back to the capacitive reactance of the capacitor, right? So I'm going to go 18 squared, subtract that from the 14.6 squared. That gives me 10.53. Sorry, I don't have much room there. 53 amps. And I know that's lagging because it's told. This overall circuit is lagging as indicated. So I can now find my IXC. So my IXC equals my IXT, or sorry, my IXL subtract my IXC. T. So the current in the capacitor is equal to the current in the inductive portion of my motor subtracted from my IXT, right? Because I know my IXL is greater than my IXC based on this information, right? Super important. So I take the 17.171 amps, I subtract that from the IXT, 10.53 amps, and that will give me my IXC. Which works out to be 6.64 amps. Okay, so my IXC is 6.64 amps. So now I want you to think about that for a moment, right? So my IXL is 180 degrees out of phase with my IXC, right? So if they're 180 degrees apart, we always take the lesser from the greater for the resultant. So in this case, we're working backwards. So it's important for you to understand that in order for me to find my IXC, I would have to subtract my IXT, right? So it depends on how the circuit is built. Sometimes you're working this way towards an IXT, but in this example, we have to use the IXT and work it backwards. That's why it's super important to recognize that incoming current is lagging. And because it's parallel, it has to be in reference to the currents, right? IXL is greater than IXC for my I total to be lagging in a parallel RLC circuit. I cannot stress that enough to you guys. Okay, so now I have my IXC. I can solve for my XC by using my Ohm's law. I know my voltage across my capacitor is 120 volts. And now I know my current, so I can solve my XC. So XC equals voltage, E total, divided by my current of the branch, right? My IXC. So that's 120 volts. Divide that by my 6.64 amps. And that gives me my XC, which is 18.07 ohms. Okay, so now I have my 18.07 ohms. The question wants my capacitance, right? So they want to know the microfarad rating of that capacitor. I've solved for my capacitive reactance. So we need to transpose the XC formula. XC equals 1 all over 2 pi FC. So whenever you have to exchange C and XC, all you have to do is swap them out. So in essence, our new formula is going to be C equals 1 all over 2 times pi times frequency times XC. And don't forget the 10 to the negative 6 because we're dealing with the unit of measurement for micro, right? Capacitors are always rated in microfarads. So that would be punched into your calculator like this. So 2 times pi, frequency is 60 hertz. Okay, times my capacitive reactance, which is 18.07, and we're applying the 10 to the negative 6, and then we're inversing that value to find our capacitance, right? So 2 times pi times 60 times 18.07 exponent negative 6 equals second function x to the negative 1. My capacitor is 146.7 microfarads. All right, so I hope that helps you guys in the understanding of how to solve that part of the circuit. So if I block that off, there it is. Okay, so if you need to connect with me, let me know and we can connect online, all right? So I'm going to show you again the solution. No Academy Awards here, but hopefully you're getting the gist of this, okay? Take care. Bye.